Hey, it's Mrs. Weefy, and I'm back to talk about double replacement reactions. So, in a double replacement reaction, we have two compounds made up of two opposite charges, and as we see, we have our two couples here, two famous couples, in fact, made up of two opposites. We see that and then in our products, we'll see that our couples have exchanged places, forming two brand new pairs of couples. That is a double replacement reaction. In a double replacement reaction, and again, we've talked about this before, you have two ions, or you have ions of two different compounds exchange places in aqueous solutions, forming two new compounds. What's key here is that you have four different ions, okay, as I have highlighted. We take the positive of the first is going to react with the negative of the second, so we're forming substance AY. We're taking positive of the second compound and forming a bond with the negative of the first, forming substance BX. So those four ions are exchanging places, forming two new compounds. We have three different kinds of double replacement reactions. The first one is the formation of water. Now, the type of double replacement reaction is determined by the type of product that it is forming. In this case, it's the formation of water, called an acid-base reaction because you have an acid reacting with a base, or it's also called a neutralization reaction for the same reason. An acid is reacting with a base, neutralizing one another. Alright, so let's take a look at this. We have a base, sodium hydroxide, NaOH, and what tells us it's a base is that OH. We talked about that before. That's an aqueous solution, and we're going to react that with an acid, let's say hydrochloric acid. And I mentioned before that acids are aqueous solutions. Now, what I want you to do, just like in single replacement reactions, is put the charge above. So we have a positive one on the sodium, negative one on hydroxide, positive one on the hydrogen, negative one on the chlorine. So let's take our positive of the first, react it with negative of the second. Correct formula, positive one, negative one, that gives us sodium chloride, which will be our aqueous solution. Then we're going to take the positive of the second, react it with negative of the first. That gives us HOH, and HOH is otherwise known as water, which will be a liquid, not an aqueous. Water doesn't dissolve in water. Okay, it's liquid. And so this identifies the product, okay, the formation of water, and that's a type of double replacement reaction. You have a base reacting with an acid, forming water. Now, our next type of reaction, oh, by the way, that's already balanced. Our next type of reaction is the formation of a gas. So and again, the product is going to be a gas. So we're going to take iron 2 sulfide, which is FeS. We're going to force it to be an aqueous solution. We're going to react that with hydrochloric acid. It's going to be aqueous, but not always, which we're going to learn. Write our charges above, +2 on the iron, -2 on the sulfur, +1 on the hydrogen, -1 on the chlorine. Iron is going to react with the chlorine, going to give us FeCl2, which will be our aqueous solution. And then the hydrogen is going to react with the sulfur, giving us H2S. Now, notice you have an acid being formed. An acid as a product will result in a gas. So this is a really important rule. That's how you determine whether or not a gas is being formed. An acid as a reactant, as we see here with the HCl, is aqueous, but an acid as a product will be a gas. Okay, Now our third type of reaction is a little bit trickier because we have to use the table solubilities. This is where we have the formation of a precipitate. And remember, precipitate is a solid formed during a chemical reaction. How do we know that a solid is going to be formed? Well, we have to use that table of solubilities. And it looks like this. It's your reference table, so you need to have that out. And if we take a look, if you don't have it out, pause this video. Alright, get out your reference table so that you can look at it. Alright, the key thing here is, what do these things mean? This is not a word search. In the initial note, okay, very important, because the initial note, these ions are not listed in the table down below. So anything that has sodium, potassium, ammonium, chlorate, nitrate, any of those ions in a compound, okay, are soluble in water and will be aqueous solutions. And to this list, we're going to add lithium. So make sure you do that. Now, these are codes that we find down here in the table. Any substance that is soluble in water, okay, down here in this table will have an S, a capital S. And that means that it will be an aqueous solution. Any substance down in the table that has a P, there are two possibilities. If it is a reactant, so guys, you have to know what your reactants products are. If it's a reactant, it will be an aqueous solution. However, if it's a product, then it will be a solid. And remember, we put an S after the solids. Anything with an I is insoluble in water, so we would give it an S, solid. Anything with an A, whether it's capital or lowercase, is insoluble in water, so it would also have a solid. Make sure you're writing these things on your table. A capital X means it doesn't react, or it doesn't exist, or it decomposes in water, so therefore this reaction will not take place. Other things too. Cupric, this is Cu with a positive 2 charge. It also applies for copper with a positive 1. Ferrous is iron with a positive 2. Ferric is iron with a positive 3. Mercurous, this is mercury with a positive 1. Mercuric, mercury with a positive 2. Stannous, this is tin, positive 2. Stannic, tin with a positive 4. Okay, now that we have that straight, let's take a look at this. If you have something like barium bromide, okay, come over here to barium bromide, we see that it's an S. We go up here to our table, and anything with this S will be aqueous solution. But notice that barium carbonate is a P. Well, if barium carbonate is on the reactant side, come up here to the P. If it's a reactant, it will be aqueous, but if it's a product, it will be a solid, okay, precipitate. Anything with an A, as we see here, capital A, lowercase a, when you come up here, we'll notice that you're going to give it an S, meaning that it's a solid. It's a solid will be formed during the chemical reaction. And then we have all the X's here that will show us if it's that substance would be a no reaction. Okay, let's take a look at an example. Let's say that we have lead to iodide, or lead to nitrate, which is aqueous, and we're going to react that with potassium iodide, which is also aqueous. Now, you might question, why is it aqueous? If we go back to our table solubilities, we'll see that in the initial note, anything with nitrate, so the lead to nitrate, is aqueous. Potassium iodide, potassium is in the initial note, so it is also aqueous. Okay, so just like in our other double replacement reactions, let's put our charges above. Alright, and then do the equation. So lead is going to react with the iodide, giving us lead 2 iodide, PbI2. Alright, and then potassium is going to react with nitrate, giving us potassium nitrate. Now, we already know that both potassium and nitrate are in the initial note, so that tells us that is the aqueous solution. But if we go back to our table, we'll see that lead, right here, go over to iodide, which is right here, it has a capital I. And going up to our table, we see capital I is insoluble in water, so it is going to be a solid. And anything that is a solid is our precipitate that is formed. So this is our precipitate. Now, why is that important? Because if you have two aqueous solutions, or let's say two aqueous products, you're going to have a no reaction. So you either have to have water, you have to have gas, or you have to have this precipitate to have a double replacement reaction actually take place. Let's take a look at this. We have sodium nitrate. Both sodium and nitrate are in the initial note, so they're aqueous. We're going to react that with potassium chloride. Potassium is in the initial note, so it's aqueous. This is +1, -1, +1, -1. Ions are going to exchange places, so we're going to get sodium chloride. We know sodium is in the initial note, so it's aqueous. Potassium is going to react with nitrate. Both potassium and nitrate are in the initial note, so it's aqueous. Two aqueous products, you have a no reaction. Okay, so that's it for this video. This is Mrs. Weethy, so long for now.